We are going to start looking at exponential functions, and we are going to first examine what exponential growth looks like. Okay, now an exponential function has the variable in the exponent. Do not get this confused with polynomial functions where you might have like x cubed plus 2x squared. That is not an exponential. In exponential, the variable is the exponent. So b will be some form of number, and that is called our base. And it's a positive number other than 1. So I could have 3 raised to the x. That's an exponential function because the variable is the exponent. Okay, now when we have f of x is equal to a times b to the x, if a is greater than 0 and b is greater than 1, we get what's called exponential growth. And basically that means our function is going to be increasing as we go to the right. It's going to be growing. Now, if a is greater than 0 but b is between 0 and 1, then we're going to have exponential decay, and we will talk about that in a later video. So for now, we are going to be focusing on that type of function where b is bigger than 1 and a is greater than 0. So here's our first example. When we are graphing these, we can get a general idea of what the function is going to look like by doing a table of values. Now, when you do a table of values, you want to pick positives and negative numbers. So I'm going to go ahead and start with -3, -2, -1, 0, 1, 2, and 3. Now you have to pay attention to what you're doing here because 3 raised to the -3rd is not -27. Remember, your rule for negative exponents means that you have to cross the line and flip the sign. So I really have 3 over 1 right now. So with a -3rd power, that's going to be 1 over 3 to the 3rd. Well, when you do 1 over 3 to the 3rd, you have 1 over 27, which is approximately 0.037. So we're going to put a 0.037 here. Then when you do raised to the -2, that's really 1 over 3 to the 2nd, so 1 over 9. Well, that's going to be 0.1 repeating. And then when you have it raised to the -1, so 3 to the -1, that's really 1 over 3 to the 1st, which is 1/3, so that's 0.3 repeating. And now to the 0. You have a property for anything raised to the 0, and that property tells us that any number we take to the 0 power is 1. Now when we plug in our positives there, 3 raised to the 1st power is just 3. 3 raised to the 2nd power is 9, and 3 raised to the 3rd power is 27. So let's start by graphing those. So I'm just going to plot each one of those points. Okay, now when I tried to plot my 3 to the 27, my graph didn't go high enough, but I know it's going to be up there somewhere, up very high. Now if you look at this, the graph starts increasing very, very, very slowly, and then it increases very rapidly. That is typical of your exponential functions. One thing we need to talk about is we do have a horizontal asymptote here, and that is going to be right here where y is equal to 0. So an asymptote is a line that your graph approaches as x approaches infinity or negative infinity. In our case, it would be negative infinity because it's approaching it to the left. Now, the reason we can't actually ever get this equal to 0 for our y values, because if I set up 0 is equal to 3 to the x, there is no value, no exponent that I can plug in there that will get me a 0 back here. And the reason for that is you might think, well, a negative. But remember, our property for negatives says that it just brings it to the bottom. So I would have 1 over 3 to some x value. That's not going to end up being 0. It's going to be really, really close to 0, which is why it's an asymptote, because it approaches it, but it won't actually ever get to 0. So that's our first graph for our exponential function. Okay, here's our second one. We have 0.1 times 2 raised to the x. I'm still going to do a table of values, so I'm going to start with my xy chart, and I'm going to do my -3, -2, -1, 0, 1, 2, 3. Now, one thing you have to be careful with is the 0.1 is not attached to the exponent. So when you're plugging these in, you have to do 2 to the negative third first, and then times that by 0.1. So I would have 0.1 times 2 to the negative third. Well, 2 to the negative third, since it is a negative exponent, I have to do 1 over 2 to the third. So I have 0.1 times 1/8. And when I do that out, I'm going to get 0.0125. Then I'm going to do the same thing with the negative 2. I'm going to plug that in and then do the same thing with all the rest. Once I get my table of values filled in, I'm going to come over here and just plot each one of my points again. Now when I did my scale, because my numbers over here were so small, I did not go by ones, I actually went by 0.05s. So I plotted all my points, then I can go ahead and sketch my graph in here. And if you notice again, I have that asymptote right here, the horizontal asymptote at y is equal to 0 for my asymptote. So it's going to get really, really close to that, but it's not ever going to hit it. Okay, we have one more example here for a graphing. This one's going to include some shifts in it. So if I do my table of values again, and I do my -3, -2, -1, 0, 1, 2, 3, when I plug these in, I'm going to have 3 raised to the -3 plus 4 plus 2. I have to do this part of my exponent first. So -3 plus 4 is 1. So I have 3 to the first power plus 2, which gives me a 5. Then when I do a -2, so I have a -2 in here, add it to 4, and I get just a plain 2. So I have 3 squared, which is 9, and that's going to give me an 11 back. Go ahead and fill in the rest of these values for the table. Okay, as you started to fill these values in, you probably noticed that your numbers started to get really, really big, and we were kind of missing those smaller values that approach our asymptote. Well, the reason for that is because we have a shift here. We have a horizontal shift of 4 to the left. So instead of picking -3 as my lowest value, I might want to go even 4 more below that and do like a -7. And then maybe a -6 and a -5. Because I'm not going to graph 245 on this. Now if I put my -7 in there, I'm going to get 2.04. If I put -6 in there, I'm going to get 2.1. And if I put -5 in there, I'm going to get 2.3 repeating. So those are going to be a little bit easier for me to graph. Now, my numbers are still pretty big. I'm not going to do 0.83, I don't think. And I am actually going to move where my y-axis is. I'm not going to put my y-axis there anymore. I am going to put my y-axis clear over here, so I have more room on the negative side in the quadrant 2. So now if I plot these points, if I go -7, so 1, 2, 3, -7 and then up to 2.04. And then -6 is to 2.1, -5 is to 2.3, -3 takes me clear up to 5. Okay, I'm not going to graph -129 either, because that's going to be clear up here again. So now, things have changed a little bit. Notice how my points right down here are already starting to level out. Well, that's because my asymptote has changed. Normally, my asymptote is right down here, where y is equal to 0, but I have a vertical shift of 2 up. So that means my asymptote was shifted 2 units up. So my asymptote is now at the line y equals 2, because that's my vertical shift. That's my k value. We've had these vertical shifts when we did parabolas, when we did absolute value functions, when we did root functions, when we did cubics. So we've had these horizontal and vertical shifts quite often. And now the same thing, the reason my points are farther to the left is because I have a shift of 4 to the left. So everything got shifted 4 to the left and 2 up. So now that I have my asymptote in there and my plots, my points plotted, I can sketch my graph in there. Whoops, it should not come up there. Okay, now with exponential growth, one of the most common formulas that we have is for compound interest. And when we talk about compound interest, we're talking about usually an investment and how much money you're going to have if it's compounded a certain number of times of years at a particular rate, and then you leave it in there for several years. For the way I wrote the equation, I let the t equal the total. So that's the total amount of money you have in your account. When you invest a principal amount of p, so that's your beginning amount that you put into this particular account. The r is your interest rate. Now, it has to be a decimal when you use it in here. So if you get 6% interest, you would put in 0.06. The n, notice n occurs twice. N is the number of times it's compounded per year. So if something is compounded annually, that would be 1 time per year. If it's compounded quarterly, that would be 4 times a year. So n is the number of times it's compounded a year, and then t is the number of years that you leave the money in the account. So we will be using this formula when we look at things that are compounded. So here's our last example. It says your bank was doing a promotional event for their 50th year anniversary. They were offering 7.3% interest on a 12-year CD compounded semi-annually. How much money would you have at the maturity of the CD if you were to invest $2,000? Now when it says at the maturity of the CD, that means at the end of this 12 years. So the first thing we need to do is we need to take our formula here and apply it to this problem. So I'm just going to go ahead and rewrite the formula here. And then we're going to go ahead and fill in our information. The question says, how much money would you have? So we are looking for t. And our p is our principal. That's the initial amount we invested. So we have $2,000. 1 is 1. And now r is our interest rate. We have to use it as a decimal though, so this 7.3 we have to move the decimal place 2 spots, so we're going to use 0.073 divided by n is the number of times it gets compounded, so semi-annually means it gets compounded twice a year. And then I also have the n again here, and the t represents the time it's left in there, the number of years. Well, for this one it's 12. Okay. Once you start to simplify that, start on the inside of the parentheses. So you need to do 1 plus the 0.073 divided by 2. And when you get that, you have 1.0365 raised to the 2 times 12. Now I need to move my exponents. So I'm going to go ahead and multiply those exponents out, because 2 times 12 gives me 24. And then I'm going to take my 1.0365 to the 24th. So next I have to do this piece right here, so raise that to the 24th power. I'm going to come up here. So then I end up with 2,000 times 2.364086. And then multiply that by 2,000. And at the end of 12 years, you would have $4,728.17. So you made $2,728 was the amount that you made on that investment. That would be our total after the 12 years, just for letting our money sit there. Now, one thing you have to make sure you do is that you follow the order of operations on this. Make sure that you do not multiply the 2,000 in until this exponent is taken care of. You have to follow your order of operations.